I've given you a simplified picture of floating point operations on x86. If you look out on the web for other information, or if you start disassembling programs, you might, as usual, see some of the history behind the development of floating point support. And that history is that originally there was no floating point support on the original 8086. Any floating point operations or any sort of inexact arithmetic would have to be implemented in software. Right? So we know how to manipulate bits, and you can take those bits and do your own addition and multiplication and so on them. And it's relatively slow, but if you only need a little bit of floating point, that's fine. But of course, modern programs pretty soon had lots of floating point. And so the 8087 coprocessor was introduced. So that means when you got a computer, it would have an 8086 and an 8087, and they would talk to each other. The 8086 would recognize the instructions that correspond to floating point and ship it over to the 8087 because floating point arithmetic is complicated, and it was as complicated as the main CPU at that time. This went on for a while. By 83, 86, then they started to put these two parts together in an integrated, just a single chip. But still, you had some chips with FP support and some without. Um, and it was only by 84, 86 that you could really always rely on floating point being available. At this point, of course, that was quite a ways back, so most software assumes that floating point is going to be available, that you're on a 386 or up with floating point support. Even though it gets integrated into the 486 chips, still the instruction set tends to be called x87 floating point support. Harking back to the coprocessor's number, an unusual feature of it is that its native floating point format is not 32-bit float, or 64-bit double, but 80-bit extended precision format. And it's not quite the same encoding because there's one extra bit that's used in a weird way. 64 bits for the fraction part, 15 bits for the exponent. So you can represent a considerably wider range of numbers using this extended precision. Um, Another unusual feature is that the registers are not numbered 1, 2, 3. Instead, the floating point registers are arranged in a stack, and the various operations work with the topmost thing in the stack and maybe something deeper in the stack, and you push and pop onto this very short stack. There's only 8 of, it's a stack 8 deep to manipulate floating point numbers and multiply with them. Right? And they'll also end up with operators that either add two things and leave the result on the stack versus add two things and sort of pop the operand before it pushes the result back on the stack. So that's the state of floating point by the mid 90s or so on. But 3D graphics and things, other scientific applications, they needed parallelism. They needed more performance that was available. And Intel and AMD both started providing this kind of parallel support. And these APIs were kind of merged by around 2000, 1999 or 2000, into the SSE2 instruction set. So chips from 2000 or so going forward generally have SSE2 available, even though these instructions were originally written to give the kind of parallel operations we saw before, the add-p and mul-p. They've become the main way of doing floating point, at least in x86 64, where it's always available. But 32-bit x86, the ABIs, programs are just written to run on relatively old machines still to accommodate those machines. And so you'll still see quite a bit of x87 code, particularly in the 32-bit mode. We are, of course, on x86 64 for all of our work, so we always have SSE2 available, and we can use that, and GCC assumes that and generates suitable instructions. And if you're looking at the machine code, you recognize that you're using SSE when there are operations like add-s, to add floating point numbers using registers like XMM0. You see move D for double precision floating point, and conversions like CVT. But x87 is still around, not only for backward compatibility for running 32-bit applications on your modern chip, but there are still some applications that can benefit from those extra 80 bits that were available in x87. So even some modern 64-bit programs we'll still use x87 instructions to take advantage of the 80 bits of precision. And you know you're seeing x87 code when you see operations like fadd or FLD, floating point load, or floating point integer load to convert. The ones that start with an F there are x87. And just to wrap up the history a little bit, it continues on after SSE2. There was SSE3 and some other variants that added new instructions. And then as computers have gotten bigger and the number of transistors is growing, then more parallelism could be supported. The registers could be extended from 128 bits to 256 bits. So the newer processors with AVX, that means SSE-like instructions, but extended out to 256-bit registers and the wider paths that are allowed by that for multiplying 4 doubles at the same time instead of 2. AVX2, which is especially new, adds some new instructions to sort of fill in even more things that can be done. We will, for the most part, restrict ourselves to the simplest SSE2 and mostly use the sequential operations, not the parallel operations.